I want to welcome everybody who's taken some time today to join us for our first presentation on Gemquest in 2025. We're now entering our fifth year of broadcasting educational gemological information from the world's leading authorities to you. And I'm hoping that this year will be just as exciting and interesting as all the years previous. As you may or may not know, Gemquest is a nonpartisan, nonprofit programming that has been established to try and share with those who have an interest in gems the newest and the most recent information, and sometimes some of the oldest information, as it turns out. This is the month of garnets, January, the month of the birthstone garnet. And garnets are, for the sake of information, one of the supergroups in minerals, which means there are many different compositions found in nature. And they all form mixtures among themselves. But very often, the trade does not use chemical analysis-based names, but people come up with marketing-driven names like rose garnet, crimson garnet, dragon garnet. Whoa. We will go through the most common names, or at least not me. The program today will go through the most common names that are around, try to assign them to the real chemical species, and of course, have a look into how to identify garnets properly with and without expensive tools, and discuss the limitations of some gemological devices due to physical properties of garnets, such as refractive index. Now, this isn't the first time we're fortunate enough to have Dr. Clemens Schwartzinger being our presenter. My name is Ray Hill, and we both welcome you to the program. And I want to first of all thank Dr. Schwartzinger for his efforts and to put together this presentation today, because he's a very busy guy, and I can't imagine how he found time. He is a researcher at the Johannes Kepler University in Linz, Austria, and a specialist in spectroscopy, which he also applies to minerals and gemstones. Besides that, he's a world-class gem cutter, having the designation from the AGT as Grand Master, and runs a small gem cutting house of the highest quality of colored gems. One of his major goals is to generate knowledge and share it with others, scientists and laymen alike. After working with tanzanites and zoisites for so many years, he again focuses on garnets and was awarded the American Gemological Association Research Grant in 2024 for his work on East African green garnets, also known as savarites or Marilani mint garnets. So, without any further information, I hope you're going to enjoy the good work that Dr. Schwartzinger has put into the talk today, and you'll learn things that perhaps you didn't know, and he'll reinforce the things that you did. Please welcome Dr. Clemens Schwartzinger.
Thank you for the introduction, Ray. And I'm just trying to start my presentation. And here you go. So today, as we still have the month of January, I'm talking about garnets, their names and their identifications. Just get a request for recording the session. So we do record it for everybody and post it also. I'll send you the link, or Ray will send you the link per mail, and I'll have it in the end of the presentation. So, but if you want to record it yourself, feel free to do this as well. So garnets, their names and identification, which means I'm putting a stick in the nest of bees, because the only thing that people will agree that there is no agreement on nomenclature of garnets. Okay, and it does not work like it should work. Okay, just an overview, because it is sometimes a boring topic and we have lots of theory and formula and a little bit of science behind it. So I tried to make it a little bit more colorful and tried just to place small pictures of garnets across all of my talk slides, as long as there's not a general topic or a general picture of garnets in the center. So here's what we're talking about. Garnets, you can find them in each and every color of the rainbow. And this is really true in each and every color, even in blue. We will see one example. Also in this picture, there are a couple missing because you never have all of them at the same time at the same place. But you see them in yellow, in green, colorless, and of course, all shades of red and pink. Now, why am I giving the talk? What is the the spark that ignited my let's say my thinking to educate people about the nomenclature of garnets. I had a friend and he sent me a message. A client bought a red pyrope garnet from me and the lab said, it is rhodolite. Can they really mix up those two? What do you think? Yes or no? Is it possible to mix up rhodolite and the pyrope? Well, yes, of course, it is easy to mix them up. Or to be more exact, it's not mixing them up, it's just two different names, because pyrope is the end member of a group of minerals defined by the International Mineralogical Association and has the formula of magnesium aluminum silicate. Rhodolite is a trade name for rose red garnets, comes from the Greek word rhodon, meaning rose red, and it is a composition, it's a mixture. It's a mixture of 70% pyrope and 30% almandine. So speaking correctly, if you say the name should be what you have at least 50% in your mixture, then any rhodolite is a pyrope. And therefore, the lab is probably right in naming the material that was sent to the lab as rhodolite, but it's also right to sell them as pyrope. This is the problem that we have. Lots of names around, and who is going to know all of them and all the funny stories about this? So I will start with the history. I mean, garnets are known for a very long time. And at the beginning, in antiquity, people called red stones carbuncle. Carbuncle was all of the red stones they found. This was mostly garnets, but also rubies and spinels. In terms of pricing, a big difference today, but then red stones in general were very valuable, and they didn't care if it's a garnet or if it's a ruby. The name garnet comes from the Latin word granatum. Granatum, as in pomegranate, means grain or seed, or also pomegranate. And you can see here, this is a pomegranate, and the interior, the seeds, they look like the garnets on a natural specimen. This is where the name comes from. In German, it's even more clear because granatum and granat relates directly. In English, it has been translated to garnet. It has been used for more than 5,000 years, like in Egypt, in the Roman Empire, in the Middle Ages. In traditional European jewelry, it is very often worn together with silver and with traditional dresses in Austria, Bavaria, also Bohemia. And they have been known for a long time as Bohemian garnets. So this is what you see here, these dark red, slightly orangey garnets. These are Bohemian garnets. Fun story, part of the Bohemian garnets comes from Austria. And of course, it's the birthday of January. We have had these already. But it's not only an old mineral. Some varieties of garnet have, I say, rather recently been discovered. Like, oh, sorry, I just see that there is a typo. It's not tsavorite, it's demantoid. Demantoid was discovered only in 1856 in Russia, where it was named demantoid because of the reminiscence of diamond. It has sparkle, it has fire, and it was nice green. It was the only location where this stone was found for more than 100 years, until in the 1990s, a second source was found in Namibia, and in 2008, a third one in Madagascar. There are a couple more nowadays, but these are the three major sources for demantoid. And you can see them in traditional old jewelry pieces. Fabergé, for example, was very famous to use this material, but also in modern jewelry, you can find here. This is Namibia, for example. The other ones on the right side are from Russia. So in history, it can go from here to there. But what are garnets? As Ray already mentioned in the introduction, it's a supergroup of minerals. And a supergroup means always there's not just an exchange of one or two elements, but there is a lot of composition and they have the same crystal structure. And the same crystal structure is now here in terms of chemistry. We have an X 3 times, we have a Y 2 times, a C 3 times, and a Phi 12 times. Every mineral that can be put into this formula is now within the supergroup of garnets. And what is special is the position that we find all those. So the Phis are the one that build up the lattice. And in this lattice, you have always empty sites. and they can be with different coordination. For example, in the X side, you have an 8-fold coordination, meaning that you have 8 atoms surrounding the M2 plus. The Y is where we have a 6-fold coordination, and is a trivalent metal ion, and the C usually has a 4-fold coordination, is a 4 times charged metal. For garnets, we have just one part of this supergroup. I don't talk about all of the others. In our part of the supergroup, we have the C silicon and the Phi is oxygen. So we can put it in this formula like the X3, Y2, Si3, O12, or the more common is the X3, Y2, SiO4, that's the tetrahedrons, 3 times. So this is the silicate. You can have, instead of the oxygen, hydroxy groups, even halogen atoms. You can have, instead of the silicon, other combinations, part silicon, iron, mixed with other elements just to make up the 4+ charge. This is everything outside of the garnet group. All the garnets are SiO4 3 times, and then we have a trivalent and a bivalent cation in the middle. And this is how the structure looks like. So the red dots that we see here are the oxygens. Then we have here, let's start from the back side. So the blue ones are the silicon, and one silicon is always wrapped by 4 oxygens. Then we have the greens, the Y sides, which have 6 oxygens, and then we have the brown ones, the X, that have 8 oxygens surrounding them. And here on the left side, you see again, the Phi is always the oxygen, the C is silicon, but for X and Y, we have different options, like the 3+ ions can be aluminum, iron, chromium, vanadium, in very rare cases also scandium. And the X side is typically occupied by calcium, magnesium, manganese, iron, or sometimes also yttrium. So not only the common ones, but there are also strange members in this garnet family. Now we have to start with the scientific classification, because the scientific classification is the one that is for 100% sure. No matter if you believe, I mean, there's a nice quote that I would like to repeat here. I don't believe in science because science is nothing to believe. Science is there, science is real. And this is the way how everybody in the world can come to an agreement. This is the same composition for the garnet, and therefore it is the same name. Therefore, we start with the easy ones. So scientifically, we speak of the group of garnets, and we subdivide it into 2 subgroups, the pyrrole spits and the eugrandites. These are again subdivided into 6 end members, and these are the 6 end members you are most likely to encounter in gemology, gemstones, or minerals. We will see that there are even more than those 6, but to start with, we take it easy and just stick to these 6 different garnet members. So we start with the first one, which is pyrope. Pyrope has a magnesium on the X side and aluminum on the Y side. The almandine has iron on the X side and aluminum on the Y side. The iron, you have to be careful, here is charged 2+. Spessartite has manganese, aluminum. The colors of these boxes are approximately the colors that you will find in your typical pyrope, almandine, or spessartine. Now, if you take the first letters of these 3 names, pyr, al, spess, you come up with pyrrole spites. So this is the name for these 3 garnet end members, and what they have in common, they have the aluminum here in the second position. The first metal can change. Now the same with the eugrandites. You start with uvaroite. We have calcium chromium silicate, grossular calcium aluminum silicate, and andradite calcium iron silicate. So what they have in common is the calcium in the first place and a different trivalent ion in the second place. What is special here is the grossular, because grossular has calcium and aluminum. So the aluminum would also fit into the first group. This makes grossular some kind of a specialty under the garnets. Okay, I was talking about nomenclature. So where do all these nice names come from? Well, either they're history related, or they come from the color, or somebody has realized, okay, we had some wonderful, valuable comments by some guy, and in his honor, we will name a mineral species like this. So pyrope comes from the Greek word pyropos, which means fire-like, and it stands for the deep red color. So pyrope is the original garnet that mostly has been used in antiquity. It's the Bohemian garnet. Almandine was already mentioned by Pliny the Elder, and he named it alabandic carbuncles because they were cut and polished in an ancient city in Alabanda in Turkey, and therefore comes the name red stones from Alabanda, almandine. Funny thing is, the pyropes were the original Bohemian garnets, and the fake Bohemian garnets, the ones that come from Austria, are mostly almandine. Somebody has to mute their microphone, please, because we have some background noise. Thank you. The third group that we are talking about is spessartine, and the spessartine were first found in Germany in the Spessart Mountains, and therefore they were named after a geographic location, the Spessart. Uvarovite is named after the Russian historian Sergei Semyonovich Uvarov. The grossular is colored very often like gooseberries, and the gooseberries in Latin is Ribis grossularia, and therefore the grossularia comes the name grossular. And finally, we have the andradite, and the andradite is again something that was named after a person, and it was named after the Brazilian mineralogist José Bonifácio de Andrada de Silva. I hope I'm good at pronouncing this Portuguese slang. So this is a wonderful picture that we have by the artist Lina Jakaite, and it gives you some basic idea of the relationship of the garnets, at least of these 6 garnets that we have here. We have the pyrope, the almandine, and the spessartine. Remember, those are all those having the aluminum in the second position, and they form a triangle. So if we exchange iron to manganese, we come from almandine to pyrope. If we go from pyrope to spessartine, we have to exchange magnesium by manganese. And then we have the second triangle where we have the grossular, calcium aluminum, uvarovite, calcium chromium, and andradite, calcium iron. And the grossular is also standing a little bit in the connection between among these first 3, so they form up kind of a tetrahedron. So it's the universal link in between the 2 garnet groups. And I think this wonderful painting, or I don't know how she did it, is really great to understand how the garnets form, because you don't have only these end members, but you can have mixtures along each and every of these axes, but also in the room in between. So if we look at a little bit more scientific presentation, then we have the aluminum-bearing garnets with magnesium here in this corner of the tetrahedron. We have manganese in this corner, iron here, and calcium here. And you can separate or divide this tetrahedron into 4 equal parts, where we have here the one which is indicated in gray is the one where we have a domination of calcium. At least 50% calcium is in the X side. That means everything, every concentration or every composition that we have here can be called a grossular, because it's a majority of grossular. However, very rarely you do find pure end members of the garnet in real life. It's just a couple of them. I mean, grossular is one where we can find rather pure materials, but mostly you will find mixtures along one of these axes, and you have many, many different atoms inside the garnet. So the systematic names, we had already the first 6. Remember the pyrope, spessartine, almandine, grossular, andradite, and uvarovite. But to make things a little bit more complicated, we can also have end members. Calcium with vanadium is called goldmanite. Goldmanite is something that is used in mineralogy. However, in gemology, very rarely, because where we do have a replacement of, for example, aluminum by vanadium, we're very often talking about grossulars with a certain amount of vanadium. You can, however, also calculate it into a composition of like 90% grossular and 10% goldmanite. That would be lots of fun if you renamed tsavorite as a grossular goldmanite intermixed series. Even more rare would be if you have scandium here in the Y position, then you have an eryngoite. If we have, again, the vanadium, but in this case with manganese, momoite, and manganese with iron, calderite, magnesium with chromium, knorringtite, and calcium. And here we have a mixture of two different ions, titanium and iron. So one is 4+, the other is 2+. If you take the average, they're 3+. And then we end up with morimotoite. So this is for keeping my tongue a little bit mobile, these funny names. Something that is very often considered to be a garnet, but is not a garnet, is sholomite. Sholomite is a calcium titanium rich mineral, but in the C position, it does not only have silicon, but a mixture of silicon and iron. Therefore, it is by definition not considered a garnet. Okay, so these are the scientific names. If you understand this, you're pretty well prepared to enter the gem trade and discuss and buy things and, well, have fun with the dealers. Something that we cannot allude to the dealers are variety names. Variety names is something that you have a perfect composition of one end member or a highest concentration of one end member, but some property makes it stand out, like hessonite, for example. Hessonite is one variety of garnet. Demantoid, for example, is one variety of andradite. It's the green variety of andradite. Topazolite, for example, is the brownish variety of andradite. Where do they start? Yeah, this will be fun discussion, I think, at the end of my talk. A little bit shaded here is tsavorite. Tsavorite is not really a variety name, but it's kind of similar to a variety name because every tsavorite is an almost pure grossular. But I think many of you have heard names like the ones mentioned here. Dragon garnet, Mahenge garnet, Malaya garnet, rose garnet, raspberry rose garnet, demantoid, topazolite, tsavorite, umbalite, mandarin garnet, Fanta garnet, Merillani mint garnet, hessonite, imperial garnet, and my all-time favorite, crimson garnet. I mean, crimson garnet, I have to admit that I would say at least 50% of these trade names have been brought up by my good friend Steve Ulatovsky, because he's an excellent salesman. And if a black stone doesn't sell, you just give it a nice name like crimson garnet. I mean, these stones are really close to black. If you have a strong light, you see flashes of red coming through, but give it a nice name and they sell. So how can we differentiate all these names and how can we make sure that we use the right name or identify the right species of garnet? Funny addition, last week, and January 21st, Steve came up with another nice name, brain garnets. I mean, if you look at the right side, okay, they do have some resemblance with brains, but still, it's not necessary to have another name. They're wonderful, perfect color, excellent clarity, large material. Why just don't stick to the given name? Why just give them a new name like brain garnets? So the trade name is usually derived by one of the three things that we see here. It's either based on the locality, like a Mahenge garnet, it is found in Mahenge. Like color, if we have a green garnet, we can name it. Okay, that was a bad example, tsavorite. Like a rose garnet, for example. It looks like a rose. Or we have some phenomena like fluorescence, like a special physical property like hardness or softness in this case. So one of the three things that we have put up here is usually the reason for giving names, giving special names. And the other thing that's not written here is just money, because sexy names do sell. If you have a dark, I don't want to say the word ugly, but if you have a dark brown diamond, for example, it didn't sell many, many years ago. But if you give it the name chocolate diamond, coffee diamond, whiskey diamond, they start to sell. And this is what people in the gem trade realized. It's the names that sell. It's the story very often that sells. Give it a nice story, give it some background, and you will sell them much better than just giving them scientific names. I am a scientist by profession. However, I have to agree, sometimes it's very hard to use these strict scientific names. So the first things that we talk about is trade names that are based on localities. Probably most favorite, the most well-known garnet here is the tsavorite. Tsavorite is by definition a grossular, and it has been found by Campbell Bridges in the late or middle of the 1960s in Kenya, and then in Tanzania, or the other way around, Tanzania, then in Kenya. And it has been named after the Tsavo National Park, which is very close there. And you can call your grossular that comes from East Africa tsavorite if it is intense green. The next one would be the Merelani mint garnet, which is again a grossular, which is mined in Merelani in the Tanzanite mines, and which is the light minty green. So here we have the first discussion. Where do we have the border between a Merelani mint garnet and a tsavorite? Is it possible to differentiate them on any number, on anything else than just the difference between buying and selling? If you're buying, it's a Merelani mint because it's cheaper, and if you're selling, it's a tsavorite because it's more expensive. Not an easy topic. One extra thing with the Merelani mint garnets is that in many, many cases, they do show some fluorescence when you shine UV light on them. Another one that came up, I would say approximately 10 years ago, is Mahenge garnets, again from Tanzania. Mahenge is very well known as a spinel occurrence, but they also mined some garnets there. From the color pink to orange, very often you see color change. What is a color change? If you have different light sources like incandescent light, fluorescent light, outdoor light, or indoor light, you will see different colors. Most well known from alexandrites, but also garnets do show this property very, very often. In terms of the chemistry, Mahenge garnets are a mixture of pyrope and almandine. The Mali garnets are named after, of course, the occurrence Mali, and typically are yellow to yellowish green. Sometimes they can be a pure green, and they're a mixture of andradite and grossular. Sometimes there is the discussion, how can we differentiate a Mali garnet from a demantoid? Sometimes it's easy, sometimes it's not that easy, because very often the Mali garnets show a rather high amount of grossular inside, whereas demantoids typically are close to 100% andradite. But even in Mali, you find some end members of the andradite, and if they are green, I think there is no reason not to call them demantoid. Again, where is the border between green, to be enough green for a demantoid, or not enough green? Umbalite, again, something from Tanzania. There is the Umba Valley, where they have some alluvial occurrences of garnets, and here they mine these mixtures of pyrope, almandine, and spessartine, and they call them after the valley Umbalite. You see where the problem comes in? How do you differentiate Mahenge garnet from an Umbalite garnet? I mean, if you're there, if you find them yourself, okay, you're sure. But think about the trade. You buy them, or the first one buys them at the mine, then they go to Arusha, then they're sold to Bangkok. From Bangkok, they come back to somewhere in Africa, go to US. Yeah, and then it's best to call them East African garnets and not give them any particular names anymore. Sometimes the color is very special, and if you have special colors, you want to give them a name, like rhodolite. Rhodolite, here the name comes from, again, the Greek word rhodon, which means rose red. And The rhodolite is a pyrope-almandine mixture of approximately 70 to 30%. And this is one of the few mixtures that has been used in the trade for a long, long time. So rhodolite is the most common garnet you will find at all of the shows, unless you're looking for the green garnets. But everything that's red, reddish, pink, orangey will be most likely in the pyrope-almandine mixture and can be called a rhodolite. One of my favorites is Malaya garnet. Malaya garnet is also a pyrope-almandine spessartine mixture. And what does Malaya stand for? Well, it's a Swahili word and stands for off color. A decade ago, people were looking for red garnets and they found these orange ones and these brownish orange that nobody liked. In the meantime, things have changed, and these are among the most coveted colors for garnets to be found. And Malaya, which was actually a bad word then, is now something like a trademark. It's a benefit if you have a Malaya garnet. The other demantoid we already talked about is green. The name comes from diamond-like. It has to be green. It is mostly a pure androdite and can be found in Russia, Namibia, and Madagascar. The color, the reason for the color, however, may be different. Can be from chromium to iron. Mandarin garnets is obvious. I mean, mandarin garnets looks like the mandarin, the fruit, is a pure spessartine and was originally found in the Marienfluss in Namibia. And there they had this very intense pure orange without any brownish overtone. And those were really glowing in the light and resembling the mandarin fruit. Therefore, they were called mandarin garnets. Later on, people found also rather pure spessartine in Nigeria, but not with the same color. So they should not be called mandarin garnets. At least this is what the people say that have the original mandarin garnets. So in Nigeria, they come up with a different name. They call them Fanta garnet. Again, intense bright orange, but on a later find. If you see them side by side, you might see a slight difference. But again, what is mandarin garnet, what is Fanta garnet, and where do you put the border? And then we have a couple of garnet names that are related to the phenomena, like hessonite. Hessonite is a pure chrysolar. It's also known as a cinnamon garnet because the color is very cinnamon-like, but the name comes from heson, again Greek, and it means inferior. So it's inferior in hardness, it's inferior in density, it's the weakest garnet, I would say, and this is where the name comes from. One of my all-time favorites, I think it's now 3, maybe 4 years ago, that garnets, pink garnets from Madagascar have been found. And it's not the first time that they were found, but it's the first time that somebody used a UV light and realized some of them are UV reactive. They fluoresce under the UV light. And they came up with the name dragon garnet. Something the world has never needed, because people knew before that a certain fraction would be fluorescent, and people still do know, and they just sell them as Madagascar. But if you put a new name on this, the material that has sold, well, quite okay so far under the name dragon garnet, it was a real boost. You couldn't produce them in the same time as people were buying them. So dragon garnet was an excellent marketing gag, but is one of the worst names in my opinion, because what does it have to do with the dragon? I mean, it doesn't, dragons do not fluoresce, and there is no fire out of this garnet. And the final ones that we talk about are the color change garnets. So color change garnets are very often mixtures with a high pyrope and spessartine content, a little bit almandine mixed in, and in most of the cases, they contain vanadium. So what does a color change garnet look like? I think we have too much of a text, therefore I decided to put in some pictures. And here we have a couple of examples. The top one is a Mahengi garnet of around 15 carats. It is in incandescent light, wonderful orange, and pink to almost red in direct sunlight. Most of the color change garnets that are known have a change from gray, grayish green to reddish purple. So this is what you see in most of the cases. Very often, you also see a color shift. So what is the difference between color shift and color change? Color change, again, this is something that you will discuss with 10 people and you get 11 opinions. The color change means that I have a change from a real color. So from red to green, from red to orange, from gray to orange, from blue to green. A color shift is intensity or just a tone. So from red to pink, for example. This is, in my opinion, a color shift. An extreme color change is what I can show you here. This is a garnet that I had in my hands 2 years ago. And we did also write some article on this one. So this was photographed with 6,500 Kelvin, which is close to daylight equivalent, with some incandescent light and with 2 different LED lights, cold and warm LED lights. And you can see that it goes from a steely blue to purple to a greenish gray to a perfect blue. And this perfect blue was also this is the best description of what the stone had in natural sunlight, at least in Arizona. We did analysis of this stone and it turned out to be 38% pyrope, 40% spessartine, a little bit of almandine, and a little bit of grossolar, plus 7,500 ppm vanadium. That means parts per million, or in other words, 0.75% per weight of this material is vanadium. And this vanadium has an absorption band that is in the middle of the visible light. And depending on if your light comes in from the left or the right side of the energy spectrum, you can get one or the other color, the blue or the red, more or less. And to make things a little bit more funny, we also have synthetic garnets. I mean, synthetic garnets are usually not made to make fake natural garnets, but they come from physics research. Most of the garnets, the synthetic garnets, are used in lasers. For example, the YAG. YAG stands for yttrium aluminum garnet. We have LUAG, lutetium aluminum garnet, and GGG, gallium gadolinium garnet. A couple of others are also available. The benefit of these garnets is that they have some properties like fluorescence. Fluorescence means if you shoot the light with certain wavelengths on your garnet, it will shine up and produce light. And this light can be bundled and controlled, and therefore you create lasers. And you can change this light by doping your crystals with different, typically rare earth elements like neodymium. Neodymium YAG is one of the most used materials for solid state lasers that we have in almost everyday equipment nowadays. There's just a few things that you can operate without a laser. So on the right side, I have here a piece of LUAG, unfortunately not yet a gemstone. And this LUAG will now be seen as it is under dark light. So you see it's a nice yellow color. Then I put here aside to the right side a UV source, put again off, put again on. And then I use the UV source and directly point at the garnet. And you will just see how it looks like. It glows, and now, wow. So this is what happens if you shine with a UV laser onto a piece of lutetium aluminum garnet. So this really starts to glow in the dark. Okay, these are the names. You know a couple of the names that I've given you, and we know the chemical composition. So how can we identify these garnets? One of the questions that comes up first is, can we identify them by color? And I took this photo in the Smithsonian Institution in Washington because it really nicely shows, no, you cannot differentiate garnets by color. Because here on the left side, it starts with yellow, goes all the way bright yellow to colorless, bright greens, minty greens to the dark greens, intense greens, and all of them are grossolar. It's just a couple of below 1% in mixture of different elements that give them a different color. So pure grossolar would be colorless. And therefore, by adding a couple of elements that interact with the visible light, they can show either green or yellow, or even red or cinnamon colored. So color is nothing to use if you want to identify your garnet. What comes closest to identifying by color is so-called UV-vis spectroscopy. It is where you use ultraviolet as well as visible light, and like looking through your spectroscope, you see the same here, just that you don't have these black lines. You get some bands, and the bands are a little bit broader, and it's a little bit more reproducible than just a couple of people looking through the spectroscope and looking at the same stone. And what I did here, I've measured two grossolars, one with a minty color, one with intense green, and also two demantoids. Again, two green garnets, one from the Ural, from Russia, and the other one from Tubusis from Namibia. And what you can see here, there is one band that can only be found at the demantoid garnets. So you can separate these green garnets by UV spectroscopy. And also other features can be found here. For example, this is way sharper than in the other two garnets. Also, it's also here in the other garnets. And if you look at how does the color intermix with this spectroscopy, so the mint one and the dark one, you see that they're pretty much identical, just the height or the abundance of the bands is much, much bigger in the tsavorite compared to the minty green. So it's the concentration of the so-called chromophore, that's the element that gives the color. The concentration of the chromophore is much higher in the tsavorite than in the grossolar. Can I differentiate between grossolar and between mint garnet and tsavorite? No, because then somebody would have to define a limit like 0.7 or a color number that can be used to differentiate between dark green, the tsavorite, and the minty green. So far, nobody has done this, and it's always a discussion. Do I have to call this tsavorite, or is it not enough green to be called tsavorite? And what's the purpose about it? The purpose is about money, because tsavorite is valued much higher than a grossolar, a mint grossolar, for example. So if we want to properly analyze garnets, we have to look at the chemistry. I'm sorry, but there is no way around this. We have to identify what elements are inside our garnet. And one of the techniques that can be used for is X-ray fluorescence. So you have X-rays, you shoot with the X-rays on your crystal, you shoot out one of the electrons in your element, and from a higher shelf, there falls one of the electrons down and emits radiation. And this radiation can be monitored, and then you can assign these radiation, the intensity or the energy of the radiation to certain elements. For example, here we have calcium, here we have iron. Some like iron display more than one feature. Here we have manganese, aluminum, silicon. And then what is wonderful about this technique, if you calibrate it properly, is also quantitative, and then you can measure the composition of your garnet. Not only that you need to know which elements you have inside, but if you remember the theory about the garnet, about the end groups, you have also to have knowledge about where are they positioned. For example, iron can be iron 2+ or iron 3+, can be on the X side, can be on the Y side. And there's lots of mathematics and calculations going on that if you have this structure, then you can more or less calculate a theoretical formula of your garnet. If you know the positions as well, then you can have a real composition of your garnet. Not much difference, but just for the scientists among us, there is a possibility to do though. In our lab, we use a different system. It's called laser ablation ICP-MS, inductively coupled plasma mass spectrometry. How does it work? We have here a nice garnet. I have already my green garnets. We shoot with a laser on these garnet, and the benefit of the laser is that we only have to shoot very tiny holes. I mean, we do shoot holes in our gemstones. This is very often really a pity because the customer says, yeah, please do not destroy my gemstones. But the holes that we're shooting are very small, like 50 microns in diameter and 1-2 microns in depth. And we shoot at 3 positions along the girdle. So if you look from the top on the gemstone, you don't see it. With a microscope, you do see the craters, but if you polish it out, it's not even the second decimal of weight that you would touch. So from the material that is shot out of these garnet surface, we transport them into the plasma. The plasma is something like our sun. It has temperatures of about 10,000 Kelvin, 10,000 degrees centigrade. It's pretty much the same at these temperatures. And everything integrates, disintegrates into ions and atoms. And the ions can now then, in a mass spectrometer, be separated. We separated them by their mass, like the periodic table, they're listed in the masses, and then they're detected. And what we get is we get the greens, the yellows, the blues, and the grays. Here we have called them magnesium, calcium, manganese, and iron. And we get the concentrations. And if we have the concentrations of these elements, again, we can go into calculations and get the theoretical composition of our garnet. Now, what is the problem with this instrument? Mostly its price. You're talking about 300,000 US dollars and no upper limit. You can go as high as you want, depending on the laser that you're using and the mass spec that you're using. So this is something that you don't have in every lab. XRF is something a little bit more cheap, but has its limitations. For example, the instrument that are used for determining the metal content in gold alloys will not work for the same purpose like the garnet analysis. A technique that is also starting with the laser ablation, but is a little bit cheaper than the ICP-MS, is so-called LIBS, laser-induced breakdown spectroscopy. In this case, we have the same first step. We have the laser, and the laser creates the plasma here, and from this plasma, we just collect the diffracted light. And depending on the wavelengths of the light, we can assign them again to our elements, and we can assign the elements in this formula of the garnet. So the question now remains, if LIBS is cheaper than ICP-MS, why don't everybody uses this LIBS? Because LIBS has one problem, the limit of detection is not that good like in the LIBS, like in the laser ablation ICP-MS. In the laser ablation ICP-MS, we're talking about PPT detection limits. I mean, you know, ppm is parts per million, ppb parts per billion, ppt is parts per trillion. So you really detect the smallest amounts possible in your structures. And with the LIBS, you're in the higher ppm range. And sometimes 10 ppm can be not enough. They already induce the color, but if you don't measure them, you may lose some information. So therefore, the LIBS is nice, but not as nice as the laser ablation ICP-MS. Here's an example. We have a nice garnet. It's an andradite. It comes from Russia, from Ufalai. It's greenish. It's an andradite, so we can call it demantoid. And you may see here, these are the spots that we have shot with the laser. And here's two lines running across, or starting here from the center of the crystal to the outer rim. And we have a couple of different colors in here. Here we have brown, we have intense green, then yellow, and then again some olive colored material. So the question is, what does the chemistry look like along such a crystal? Here we have another example of such a crystal. So this is about 70 carat demantoid noodle. As they're found, it's in the center, it's brownish. Then we have the intense green, and outside a little bit yellowish. And here we have the concentration of various elements versus the position. So we start in the center where we have the brown, and we see that we have high concentrations of titanium. Titanium together with the iron, they form an intervalence charge transfer, which is very often in minerals found to be the reason of a brownish color. And when the titanium goes down, then we have here an increase of chromium. So the intense green zone, the vibrant green, is due to the chromium and not titanium. Now, if you understand this and you're a little bit trained in chemistry and physics, you can understand why people in Russia throw the demantoid garnets into an oven, because the titanium and iron complex breaks up, so the brown becomes colorless, and you see the yellowish to green coming in this position. So many of the demantoids from Russia that you have in your jewelry have been heated. The problem is you cannot detect it because it's very low temperature and there is no change in any composition. If you have lots and lots of garnets seen, then you might find some traces that indicate the heat treatment. But for most of us, it's not really likely that you can differentiate between a heated and an unheated garnet. So these are the possibilities if we identify the chemical composition of our garnets. Then we are pretty much sure what we have. However, only few of the smaller labs have those instruments available. But what most of the smaller labs have is Raman spectroscopy or FTIR, infrared spectroscopy. So I was also looking into these two techniques. And here we have Raman spectroscopy and the spectra of almandine, pyrope, and spessartine. And you see they look pretty much the same on the first glance. If you look closely, then you see, okay, this huge peak here shifts a little bit, especially for the spessartine. If you look here at this position, there are 3 peaks overlapping here, here as well. Here you see they start to be separated. So there is a difference between these garnets, and these are pure end members. We're not speaking about mixtures yet. The other 3 garnets, uvarovite, grossular, and andradite, again, those two look pretty much like the first 3. The grossular has 1 band here that comes up, which sets it a little bit apart. And the andradite now is easier to identify because you have 3 peaks here and 2 peaks here. So andradite is easy with Raman. Everything else looks a little bit similar. The question is now, can we identify mixtures as well with Raman spectroscopy? The answer is yes, because Raman spectroscopy does not look at the elements. I mean, it doesn't matter if there is a calcium and iron. Raman is just blind for elements. But what it looks like is the lattice. It looks on the lattice parameters, and if you have a larger or a smaller atom or ion inside your lattice, the lattice may be squeezed and maybe elongated the parameters. And I have a very nice example here on carbonates, and we have here magnesium, zinc, manganese, calcium, strontium, and barium, so different cations for the carbonate. And here we have the second number is the radius of these ions, so from the smallest up to the highest. And these are the spectra. They're all composed of this major peak for carbonate and 2 smaller ones. And if we look here, we can simply place a line that runs through these signals with different quality, I would say. Here we have one peak that's a little bit off, but here the major one. And you can just calculate by the position of one of these peaks, the average diameter of the cation that is inside. The problem now comes if you have a mixture of manganese and magnesium, it may also be a zinc inside. So this is something that you cannot differentiate, but for garnet, it works pretty well. Because luckily, my Italian colleague, Danilo Bersani, has written with a couple of his colleagues a software that is called MirrorGem. And this MirrorGem now takes a spectrum. You have to put in a couple of numbers from where are the peaks, how many of the peaks are there. And then you can differentiate these 2 garnet spectra. You see 3 peaks here, 3 peaks here, in the middle, 1, 2, 3, 4 small one, 1, 2, 3, 4 small one. Here we have 3, here we have more or less only 2. So there's a slight difference. But other than this, they look very, very similar. If you do the calculation, you will find out this one has 42% of almandine and 58% of pyrope. The other one on the right, 11 almandine, 83% spessartine, and 5% grossular. So this one would be, by nomenclature, a spessartine, and this one would be a pyrope. So with Raman, it's even possible to assign, under certain circumstances and with some limitations, a rough composition of your garnet. And Raman is something that is rather readily available in, I would say, medium quality gem labs. Is it possible to differentiate the green garnets? Rather easy, because here we have a tsavorite, here we have a demantoid, and the tsavorite spectrum is here in red, and in blue we have the andradite spectrum. So please don't be fooled by the huge signals that we have here, because these huge signals is fluorescence. What we have to look at is the part here from here. And here we say this is one peak where we have 3 here. Here we have a small red one. So the intensity of the fluorescence is something that is not Raman, but it's something like an add-on. And if you know how to differentiate the Raman from the fluorescence, it's extremely helpful. So a Merlani mint garnet, this one is a little bit on the brighter side, I have to admit, has a very strong fluorescence, but even without the fluorescence, if you have a dark green tsavorite versus the demantoid, it's very easy to separate them with Raman spectroscopy. The question is now, infrared spectroscopy, can this do the job as well? Yes, it can, but you have to be very, very confident in what you're doing. I have here the spectra of an androdite, a grossular, spessartine, and a pyrope. So I tried to place the names in the correct colors. So spessartine is intense orange, and the pyrope was a violet one, almost violet one. And what we can see here, well, we have some bands and some shapes that look pretty similar. So we can assign all of them as garnets. That's easy. But the androdite, again, has an extra band. We call these bands here in scientific terms here. And also here, the pyrope has very little. So this is water or hydroxy ions. So there's lots of water in these three and just very low water content in this one. So we can separate them as well. How about the mixtures? Again, we have a trend in the position of this band, but I would not try to calculate it. So you can get, this is mostly androdite, this is mostly grossular, but calculating mixtures from infrared spectroscopy is something I would not recommend. However, now we have just spectra of one of these garnets each. The question is always reproducibility, and if you have scientific work, you always need to have more than one sample. You preferentially want to go into the hundreds of samples just to make sure what is the difference. So here it's just two demantoids versus two tsavorites. And again, you see, yeah, this band here, the second band in the androdite, this is definitely something that tells us apart from the grossular, and the amount of water is much higher here in the tsavorites compared to the androdites. So this is possible, it's reliable, even with infrared spectroscopy, to separate green garnets within a couple of seconds. The measurement time here is something like 10 to 15 seconds. Now we're sliding down the ladder and coming to cheaper and cheaper equipment and to the ones that's readily available for most of us, like refractive index or density. Yeah, but here starts the problems. We have the pyropes with a refractive index 1.72 to 1.76. Almandine is a little bit higher. Spessartine, yeah, it's about the same like the almandine. Uvarovite 1.87. Grossular can be almost anything in here, can be a pyrope. 174 is also not far away from those here. And the androdite 188 to 1.94. So those experienced with refractive indices realize at once some of them are too high to be measured. They're over the level, over the top. And this is one of the things, if you have no reading on a wonderful green stone, this is a lucky choice because that might be a demantoid garnet. Some of them can still be measured, so you can differentiate a couple of those garnets, but you can never be sure because some are, depending of course on the instrument that you're using, the refractive index by itself is not limited on these machines. It's just the choice of glass that you're using and the choice of contact liquid. There are some electronic refractive index machines that are not using the refractive index but the reflectance, and they can measure androdites without any problems. The question that would be here now is, why do you have some distinct numbers and why do some have a range? Well, because sometimes I take the numbers out of literature, and if you just look through the literature, no matter which books or which websites you use, you will find a range. And the range is due to the fact that very rarely people have access to pure end members. The pure end member has just one refractive index. It doesn't have two because it's cubic from the crystal system. Therefore, there is only one refractive index. No matter how you turn it and how you change it, it's just one refractive index. But the refractive index can be dependent on the light source that you use. So if you use LED light or if you use the classical sodium vapor lamp, or you have anything in between, the refractive index might change a little bit. And what's the reason for most of these discrepancies is that you have mixtures. There's very rarely a pure pyrope. There's always some other elements inside, and therefore you have the ranges given here. So the problem is now with 174, 175, you may fall into a couple of these categories. The same is true with the density, the ranging here from 3.6 to 3.8. This one, almandine, due to the iron, has a higher density, is going up to 4.3. Also, the spessartine, 4.1 and a little bit. And the lighter ones like the grossolars, you remember the hessonite inferior because the lowest density has a density of 3.6. However, first of all, measuring the density reliably is not that easy because you need at least a second digit. And then again, you have lots of these mixtures. They fall under the linear mixing rule. So if I have a mixture of pyrope and almandine, I can calculate from the measured density. But you never know if not anything else is in between. And if you have ternary and quaternary mixtures, all your mixing rules cannot be applied and you just get random numbers. So it's nice to get a first idea about the composition, but you cannot do a definite check with refractive index and also not with the density. What can help you in some cases is a simple magnet. I mean, a simple magnet, I was using neodymium magnets. They're among the strongest magnets that are available. So if you put two of them together, you will have a hard time of getting them apart. And for example, spessartine and andradite will be picked up by the magnet. The spessartine due to the manganese and the andradite due to the iron. The iron must be here in this Y position because it's here. If it's here in the X position, it's not magnetic. Those two can definitely be picked up by the magnet. However, it of course depends on your magnet. It depends on the size of your crystals or your gems. And the others are in part also magnetic. So sometimes you can drag them along a table, for example, or you place them on a piece of paper and put this inside of water so that you have not that high friction to the surface, and then you can drag them along with the magnet. But spessartine and andradite are the only ones that can reliably be picked up with a magnet. So helps you in part. And again, something that should be found in every gemologist's briefcase, I would say, or backpack, is a UV torch. The UV torch that I'm using here is 400 nanometers, or you can also use the 366. This is pretty much the same. And we have here a nice Merelani mint garnet or a bright green telluride, whatever you prefer. I use my torch and it shines like wonderful orange. I had another one, approximately the same color, same green. And you see here the fluorescence is pinkish to red. Of course, being a scientist, we recorded the spectra. And what you can see here, let's start with the right one. This is a pure fluorescence of chromium. You see here the 700, or it could also be vanadium because it's very hard to differentiate between these two. And here on the left side, you can see, we see the same chromium or vanadium band, but also there's a second band. And this separates them. And these two mix together. Therefore, we have the pure red, pink here. And here we have the pink mixed with yellow that makes it orange. So with the UV light, you can, again, separate a couple of those garnet. For example, I was running through a batch of rough Merelani mint garnet, or not, yeah, it was Merelani mint garnets, and all of them were showing fluorescence except for one. So I picked those up and said, I want to test this further, and it showed up to be a tourmaline, for example. Very easy tool, small tool, cheap tool, and can help you a lot. So based on these results, we set up our new research project, the luminescence of green grossolar garnets from East Africa, where me and also my brother have been awarded the HEA research grant last year, and we're now working on this project, and I hope to be able to present next year the results. How can we use UV light to separate garnets from East Africa, from Tanzania, from Kenya, light greens from dark greens? What else, like, can we identify mines, specific mines out of this profile? And is it necessary to have the high-end machines that we have, or can we also transfer the to be gained knowledge then to simple and easy devices like these UV torches. So I cannot let you go, of course, without showing you some crystals, because I'm a collector of crystals also, not just cutting them. So garnets are wonderful symmetrical crystals. Here, I could ask you, how much could you identify? How many grossulars do you see? We have 1 grossular, we have 2 grossular, we have 3 grossulars. Here we have the hessonite. Here we have the gooseberry, where the name comes from, or a raspberry garnet, very often called. And this is a pure grossular, colorless. This is almandine from Austrian Alps, and this is an andradite. Now, before we start into discussion, also a link. We record all of these Gemquest talks and events, and we have an archive. And this archive can now be found on this wonderful short, I'm sorry for this, website, because this is from our university. So the link will be distributed. You can find it there. We have direct links to our YouTube channel, or you can directly check the YouTube channel. It's running under the name of CS Gemstones, where we have the most recent recorded talks. Please be patient. It takes some time to upload this. So I'm backed for, I think, 2 talks now. And we also have an archive that dates back to Jolyon Rolf's site, which is called gemdat.org. And also these can be found here on this website of our institute. So if you check this address, please be sure to scroll to the very end, and then you have also the link to the very old ones. We're still trying to sort them, to name them properly, but at least all the talks available are there for your enjoyment. With this, I would like to thank you all for your attendance and would like to open for any discussion, if it's not too harsh.
I would ask you to take a look at the chat. Clemens, I think there's some questions in there.
I'm doing the everyone generally greetings. Sarah Ritchie.
Still leave that link up for us, please.
I'll put it back afterwards. I cannot do both at the same time. Sorry.
Okay.
So Steve at New Aerogems at the Pueblo show. Yes, that's true. Any chance of hitting the mute? Okay. We need everyone to make the mute. What is it? What test? Sorry, that was what test do you perform to know that the garnet has 38 perhaps pyrop, 40% spasticity? So the test that we do is the laser ablation ICP-MS, and it's correlated with the Raman spectroscopy. So we're still working on making sure that those two give the same results. And within of a couple percent, they very much match. How much, where could I find electronic RI tester? Electronic RI tester, this reflectance tester. I know that there is a guy in Austria that produces them. He comes from Iran. I can't remember the name, but if you send me a PM or an email, I can look this up and let you know where they are available. Also, I've been trying to find old video. Thanks a lot. What causes the horsetail hairs inclusion in demantoid garnets? Okay. In most of the cases, it's chrysotile fibers. So there is very often, there is a small inclusion of chromite. Can also be magnetite, but mostly it's chromite. And then you have the chrysotile fibers, which is something like an asbestos fiber that grows from these seed and produces these horsetails. Horsetails are nice. They add value. That's the only inclusion I know of that adds value to a gemstone. And unfortunately, they were very often linked to Russian origin. I mean, it is true that most of the Russian garnets show these inclusions. However, they can not only be found in Russia, they can also be found in Canada, they can be found in Italy, everywhere where you have the garnets formation in asbestos material. Whereas they can never be found in demantoids from Madagascar or from Namibia. They just don't have the chrysotile and they cannot form the horsetails. So, okay, I think that's all of the questions. Do horsetail inclusions exist in East African garnets as in the Russians? In East African, well, I had one nice example, which was not an androdite. It was from Tanzania garnet, a color change garnet, and that contained something that looked a little bit like a horsetail. It was published also in the Journal of Gemology. It was most likely rutile needles, and they were producing something like a linear horsetail. But very rarely from time to time you can find something that is similar. But not in demantoids. Demantoids from Africa, at least I have never heard of anything that was formed there in chrysotile. They only come from calcium-rich origins, and they don't produce horsetails there. Okay, there are a couple of links to the equipment where it can be bought. For laser ablation, it will tell you which elements are present, but how do you know that, for example, the aluminum is part of the Grosler? Okay, question from Penelope. If we get the elements, but how do we get the assignment, or if there is aluminum, how can we make sure which part of the garnet it's from? So the aluminum is the weaker part. I would compare it as strong and weak indications. The first one, the X, is the most important because the X defines what it is. Then you have the aluminum, and you compare the aluminum mostly with the chromium or vanadium to get the end members. The problem that you have is the iron. And what you do is you just calculate all these measurements, you divide it by the molecular weight, so you get the atomic numbers, and then you normalize them on the three silicon atoms that you have inside. And then you get the composition like manganese 1.7 and iron 1.5, and you add those up, and this gives you more or less the end members. This is the easiest way to calculate it. As I said, in order to be perfectly true, you have to also know the positions where the atoms are. There's a question, where am I presenting in Tucson? At the USFG, the United States Faceting Symposium, which is held in the Old Pueblo Lapidary Club. And this show is running, I think, 4 or 5 days with lots and lots of interesting presentation. Best way to find out is visit Facebook and look for the USFG, United States Facetors Guild. Okay, that's all that are here. So now I can show you again the link. I mean, Ray, I'm sure that you will distribute the link in an email for those who want to copy it here. That's also possible. And now I'm open to any questions through the microphone. Are there any other questions?
Hi, Clemens.
Yeah.
Hi, this is Bernard speaking. I'm not so I don't do the separation from the garnets in the way you do. I do it with this more or less old triangle. How can I say it, is connection?
A mixing diagram.
Connection between yes, there's a table connecting the Ri index and the density, and there are several tools that you can check the approximate part. Is it more pyrope or some more almandine inside? I mean, you said it is not accurate enough, but is it enough for me to just to check it without any more expensive equipment, just for my own to separate in a cheaper way?
The question that has to be answered first is, what is the purpose of doing it?
Yes, to know what kind of garnet this is.
Yeah, again, what is the question of it? I mean, do you want to write an appraisal? Then it might be very important to have the accurate composition. If you want to publish it in literature, you have to have the accurate composition. If you just want to sell this, does it make a difference if it's 60, 70, or 75% of a pyrope?
No, I don't need to know it so exactly, but I want to know, is it pyrope, is it almandine, or is it a color changing garnet in between or something like that? And I guess there are some tables, quite old ones, to use, and I tested several where I have some accurate uh, uh, testing, and I get some more or less accurate Ergebnisse,
Results.
results with these measurements, and I think it's for a usual gemologist, it might be enough.
It is more than enough for most of the people. I mean, you just have to be, and this is something that I always try to teach people, you have to be aware what can your method do and what is impossible to do with your method. As long, for example, as you're looking at a Mali garnet, you will have a perfect fit with your simple method, because a Mali garnet is always a binary mixture of a grossular and an andradite. If you go into the, let's say, umbellites or something like these rhodolite garnets or color changing garnets, you will have lots of different possibilities. I mean, if you measure a refractive index, it can be either a binary composition of two or a tertiary composition. And in this case, you're not having a point, but a field, or it can be, if you have four end members, the field is more broad and then it gets three-dimensional. So you may be very accurate, but you may also be off. But usually you're in a range that is acceptable for most of the people. What is not possible is assigning the trade names. You will not be able to have the difference between Mahenge garnet and umbellite garnet, because you never know where they come from. And they have pretty much the same chemical composition.
But I don't want to be very wrong. And I say, okay, when I know approximately, but so I can say, okay, this might be some mixture of almandine and grossular or something like that. Yeah. So I'm not too wrong when I sell them, or when I tell you this is this type of garnet. So I don't have to know, okay, it's exactly 37%, but I know, okay, it's approximately 50-50 or something like that.
Yeah. Especially with the 50-50, it's very hard, because you give it either the one or the other name, but you're not completely off with the method. You get a good idea, and I think it's enough for selling them. It's better than doing nothing.
Yeah, I think I don't want to be very wrong, you know.
Yeah.
And it's better than say, okay, I have something to fix it, and say, okay, I can tell you why I say it's an almandine and not a pyrope, because I did this testing. And it might be not so correct, of course it's not. Yeah? But for some reason, for selling something or telling a colleague, it's better than nothing, isn't
Yeah,
it?
definitely. And for example, also if you're talking about the Bohemian garnets, I think you will have a couple of those also in your lab. It's just two possibilities. It's either the almandine or it's the pyrope. And then
Almandine is the larger one.
and it's the cheaper one. But usually it's the darker one, so you want to have the pyrope. But yes, then your test will be sufficient, I think. It's not always necessary to go over the top. But if you have a couple of things where you are, let's say, undecided, send them over to me and we'll make the final call.
I tested the gems where I have the results from some lab reports, and I did the testing with this easy methods, and I came to approximately the same result, and that was just funny to me to fix it and to have to get something I'm sure about that.
Yeah, no, it's great.
But I don't want to make some report of that, of course.
Are there any other questions?
Yeah.
Well, thank you so much, Clemens. That was an extremely thorough rendition of your experiment and knowledge about garnets to share with us. I don't think all of us can work at that very finite level, but the general level to be able to determine general classifications of garnets is certainly even now become a little more difficult, thanks to your explanation. So just to let you know, we are looking at next month, in February, to air a video that was made quite a few years ago of Dr. Joel Aram. Now, some of you may know he wrote the book called The Encyclopedia of Gems, which is the original encyclopedia of gems. I think a number of people have tried in the meantime to do that, but Joel is the original guy. And I think he gives a very good overview. He spent 6 months preparing this talk. So I think it's actually worth watching. I'm hoping you'll make an appointment in your brain to see us see this video on the last Sunday in February. So and I think you'll learn things even from this. It's a very historical and interesting program and I hope you'll enjoy it. So please come back and join us in the last Sunday in February. Thank you for joining us today. Thank you very much, Clemens, for all the work you put into this. And now we know exactly why you earned that research grant. Not a whole lot of people in the world will be able to do what you're doing.
No,
So thanks again. Thanks for coming, everybody. And we're going to sign off now, and hopefully we'll see you and your friends next month.